Hello everyone, this is Mainak, your Civil Pro, and today I'm back with yet another tutorial on Etabs. So those who are visiting this channel for the first time, let me tell you this, the pattern of my tutorial videos is such that I provide the materials which you need, like a plan, sometimes the guides, sometimes the important codes which are necessary for you to understand this properly, and then I present the lecture so that you can practice along with me and you can learn so that you can apply these professionally. There is no bait or nothing hidden in this thing that I am doing this, showing this particular thing, and some more things I'm including on my courses. Though it's true that I have some Udemy courses which you can check out, but the most of the things, in fact the entire thing, you will find here in this videos of mine, and not trying to hide any knowledge. I'm trying to share the knowledge so that all of you can grow, all of us can grow together, and if I have any mistake, that be pointed out in the comments. And in fact I've learned a lot of from all of you guys, so that I can learn and give it back. So that's the motto of our channel, and the purpose of making this videos. Okay, so let's get started. So we have today a plan, a PDF which you can download here. I provided, and basically we need to make this basement plus ground floor. So about the basement, you can have an Excel sheet to make the retaining wall. Here you can see the retaining wall in one direction. There is actually a road going on, and there will be some filling, so that's why they're providing retaining wall in this direction. So retaining wall design you can do manually here. Now I prefer to do manually, or you can have an Excel sheet. There are some Excel sheets which you can purchase also and do the retaining wall design. So that's simple, so not covering that. So we'll go design this, and above this it is a truss here, and in fact I've also designed the truss here. I'm also planning to make a video on this, but it will be a little bit long video how to make this kind of truss, because the roof design is a little bit complicated. Not it's simple, but let's say you have to apply some mind, but not today, not in this tutorial. In this tutorial we're going to the RCC part, and let's go here, because I don't think that many people will be interested in the roof truss design. Maybe I'll put in somewhere else the video of the roof truss design. Okay, so now this is a basement plus G building, and if you follow my videos, I always give you the structural design consultation, which also you can download here. I'm providing every material here. So this is general. I can just have this. So this is the basement plus single floor, and truss top height is this 2 meters and 1.4 pro truss B. So this is not important for this tutorial because I'm not designing the truss here. So 3.9 meter is the floor to floor at both the basement and then the next floor also. Plinth height is 0.30 and foundation depth is 1.5, and the total column below plinth will be 1.5 plus 3, but we'll take in higher side 1.95. As we see from soil district board is taken 130. Design will be done in Etabs software. The grade of concrete will be M25, and grade of steel will be Fe500, which will be used. Initial columns considerations were given by the architect, 400 to 400 mm. I have added some columns. I think I have this column I have added because I wanted this to be a primary connection here, and okay. This is a column which I have added, and then we have the grids. So in Etabs, the grids are in the adding fashion. So suppose the first grid is 0 here in the X direction. The next grid will be here in sorry, let me just do it properly. Next grid will be 2.8 here, and then the next grid will be starting from this 2.8 plus whatever this distance is. It will be total of 5.3. Okay, so this will be the grid pattern in Etabs. So if you are downloading from PDF, you can just downloading the PDF for practicing. You can just see from here 2.8 plus 2.5 like this, and the other distances are mentioned on the left side. Okay, so from this grids we have written this, prepared this this thing. So there are 8 number of grids in the X direction, Y number of grids in the 8 number of grids in the X direction, and now Y we have 7. So these are the grids. These grids are also given by the architect. We have an option to change it, but we didn't need to in this time. Okay, So the load considerations will be as per the Indian codes. So dead load is as per taken as per 875 part 1, and the self weight will be automatically calculated by the software. And the wall load on beams, and wall load on beams is calculated here 20 kilonewton per meter cube is the approximate load of the plaster and the wall, taken together. You can just take 19 for the bricks, which is as per the code. 3.45 is the height, so 3.9 is the height. So if this 3.9 is the height and we've assumed the beam is 450, then just deduct that and just to get this 3.45 value. And 25 is 250 mm is the thickness of the wall. So we're taking this 17.25 approx, which will be acting on the plinth beam as well as these. You can see this is kind of a roof beam, but the ground floor beams, for example, ground floor beams, and then the roof of the ground floor will have the truss over it. So the truss will look like something like this. Okay, so we are taking approximately 10 kilonewton per meter square for the truss, which is the load which will act on the this beams. Sorry. So this should be enough for the load consideration of the truss on the beams. And then we have floor finish loads, which will be 0.5 kilonewton per meter square, and this floor finish load will act on the for the floor tiles. So the floor tiles will be present here, but here we won't have any slab. So this is the basement. So here we don't need to consider. So we don't need to consider here. There definitely will be a slab. That is the roof of the basement. In the roof of the basement there will be floor tiles. So for that in the dead load we'll consider this. And obviously this is for the truss as per table 2 of the code, and this is floor finish load. This is for the RCC part. This is table 1 of the code. Okay, maybe I should update this table, but everyone knows this table 1, I think, so that's why I didn't write. So I should update this table 1 of code. And then we have the live load. Live load is as per 875 part 2, and since the building is a residential purpose and restaurants, so building is not residential purpose, obviously. Okay, so what's the purpose of the building? We'll have a live demonstration here to check the live loads here. Restaurant, so here the live load will not be required because there won't be any slab, but here it is also a restaurant. So now we'll just check into the type of the building live here. Okay, so our building is located in tourist destination, so this is a part of a tourism project. So we have to first think which will be the type of the building here. So you can see from the examples directly in 875 part 2. So assembly buildings we have civil, travel, travel and similar purposes. So travel and similar purposes comes under assembly building. So the building will look under assembly buildings for the restaurants. So we have residential, definitely is not residential. Educational, definitely is not educational. And then we have institutional, okay, and then we have assembly buildings. So we have institutional buildings here, assembly buildings here. So in the assembly buildings we have restaurants. So restaurants should have a live load of 4. Okay, so live load of 4 should be given. So here we'll just modify this load. Here live load, it will be assembly slash, in the assembly we have restaurant, and it will live load of 4 kilonewton per meter square should be acting on this. And autocorrect is winning our spelling studies. Okay, so this is as per table 1 of code. And by the way, this roof truss you'll find in table 2 of code. Okay, so this is 4 kilonewton per meter square which you have to apply, and this will also be applied on the portion where you have slab. We'll have slab here in this floor. So here it will be applied, and these are the wind parameters. So basic wind speed is 55. The location is in Tripura, so the entire Tripura is in basic wind speed 55. Terrain category 1, K1, K2, K3. We will not go deep into this. You can just look into the pages here of the 875 part 3 2015, and you can just find those things here. Seismic load also. will not go let that deep, but every parameters which you need you'll find here. Seismic zone 5, the building location is Tripura. Seismic zone factor is 0.36, and this is as per these two tables here. And soil type you will find as per the soil test report, and this classification is mentioned in table number 4 of this IS code. Response reduction factor is 5. SMRF, the building is in zone 4, we consider SMRF as per table number 9. SMRF is for SMRF the response reduction factor, or the RR, is 5. Importance factor is 1 here, okay, and the damping ratio is 5%. Vertical earthquake directions have to be considered here, obviously, because as per 6.3.3. So those who are new to this 1890-2016, so 1890-2016 has started considering the vertical earthquake effects for structures in zone 4 or 5, or even important structures in other zones as well, as you can see in this clause. And in the seismic weight, we'll add the full amount of the dead load and a particular percentage of the live load. So in our case, the live load is 4, so it is more than 3. So we have to consider 50% of the live load in this, in this particular building. And the diaphragm consideration is rigid, and then the crack section properties should be considered here. And the moment of inertia for the columns will be 70%, and the moment of inertia for the beams will be 35%, which will be taken. And response spectrum method will be used for the dynamic analysis of the building. You can just see in the definition, it's a representation of the maximum responses of a spectrum of an idealized single degree of freedom system having different natural periods but having the same damping. Under the action of the same earthquake ground motion at the basis, the response referred here can be maximum absolute acceleration. So it's like the acceleration, velocity, or displacement. So displacement, factorial, this velocity, and then you differentiate this velocity again, you find the acceleration. So this is it. And there is also a confusion around when you have the scale factor in Etabs. So the scale factor in Etabs, as per the Indian code, it is simply with this Ig by 2R. So I is the, I think I should write this in bold here. So it should be Ig by 2R. So this is Ig by 2R. So, and this is equals to I is 1 in our case into the 9.81 meter per second is in our I, we're using the SI units, and then 2 into response reduction factor is 5. So this is actually 9.81 divided by 10 in this case. Okay, this is 0.981. So you can take 0.98 here for the scale factor. So this, as per the data in the CSI official, CSI is the manufacturer of the Etabs, by the way, official website. So you should always follow the official website for the things. And then obviously if the dynamic response factor this is less than the static response factor, then you have to scale it, then that's another area. But this is basic. When you just start, we have to consider this. Model mass will be considered, and these are the checks which will need to be done as per these two clauses. So you can download this material, and these two checks need to be done after the analysis here. And this then we'll have the analysis results here. Okay, so let's go, and then we'll write the analysis results here. Whatever the results which you're finding, we'll write it here. So let's start. Okay, so let's open Etabs, file, new model, and the settings will keep the Indian settings. Okay, and obviously grid and the story will modify. Grids, let's modify first, and then we'll go with the story. So I've already written the grids here. Let me just do that. So it's 0, and then 2.8, and then 5.3, then you have 7.8, add another one, then you have 7.8, it's 10.3, then you have 12.8, then you have 15.6. Okay, we're done with this grid. And after this, okay, not done, we have another one, it's 18. Okay, done. And after this, we just do the Y grid. So it starts from the bottom, And the Y grade, just remember here it starts from the bottom, so always just start from here. This will be 2.7 and then we go on like this. Okay, so Y grade 0, 2.7, 2.7, and then we have 7.75, and then we have 12.75, and then we have 17.75, and then we'll have 20.85, and then we'll have 23.85. Okay, and then we'll edit the story data. So bottom story will go minus 1.95, plinth level will be at 0, so we go minus 1.95 here, sorry, plus 1.95, so plinth level will be at 0, and the floor to floor height is 3.9 meter and 3.9 meter once again, and then we don't need this one, so right click and delete story. Okay, done. Now we have this thing done. 3.9 is the floor height, and then we click on OK, and then we click on OK. So this is the model which has opened here. So now we'll do the model as per the plan. First of all, we will define materials here. We'll add new material, and we'll go with India, and it will be concrete. M25 is the grade of concrete which we'll use in this project. So M25, and then rebar. Rebar will go with FE500 as per our tender documents. We'll go with this, and then we'll go with the section properties here. Section property, we'll just edit the column property here. First of all, I'll write this C 400 cross 400 is the column size, M25 is the grade of the concrete, and 400 and 400 is the size of this. Property modifiers, by the way, just show you the code very quickly. I had already shown, but showing again this code. 70% for columns, movement about this axis 0.7, and again 0.7. Click on OK, and reinforcement will be taken FE500. Okay, so and then we'll edit the beam properties. So it will be B 300 into, let's see the size what we have given here. Size assumption will be 300 to 450 for the beams, and then M25 grade, the width will be 300, and this will be 450. Property modifiers for the beam, it is 0.35 for the Sismic code. Moment of inertia is 0.35. Rebar is FE500. Okay, good to go, fine. Then section properties have been defined. Slab sections also defined. We'll define slab. We'll give slab of 150 mm thickness, 150 mm. So only the load will be considered, it will not be designed. 150 mm. Here M25, and the thickness change it to 150, so that the self weight can be considered, and also we can put the loads which will be acting on the slabs, like the floor finish load and the live load. Okay, having done that, so we have defined the material properties and the section properties. Now let's jump into the load patterns. Now in the load patterns, we'll add another load called the other dead load, in which we'll add all the floor finish and the other dead wall loads on the beams and the other. So these are the dead loads which we'll add, but this will not be inclusive of the self weight, because self weight we're considering this. So we'll add new load just in case, and then we'll add the seismic load, and seismic, sorry, just misclick. So it will be 2002. By the way, the updated code is 2016, which you are using the latest version. You select that code. Okay, Seismic X will add new load, and another one Y will add, and obviously we'll add another wind load here, WL, and we'll go wind here, and WL wind, doing a lot of misclicks play. Just select the wind load code, and then click on add new load, and then click on OK. Okay, this wind load and Sismic load are added here. I'll save the model here in the desired file location. So after that, the dead loads and live loads are added here, and also the seismic and wind loads. So then we'll define the seismic mass, go to define, and we'll go here, go to mass source. Mass source, we know that it will be dead load plus 50% of the live load, since the live load is more than 10, which I've already told you. So not repeating, just read the additional element self mass and include the specified load patterns here. That's my style. Dead load obviously will be added, and the other dead load will be added. So these two will combine be the dead load here, and the live load will be 50%, 0.5. Since it is more than 4 in the seismic mass, it will be added, and then it will click on OK, and then click on OK for the loads seismic mass to be defined. So after that, we'll define the response spectrum function. Go to define, and then we'll go to function, and then response spectrum function. Just delete the existing function, and we'll define as per our IS code. And you know why I take so much time to find the IS code, I don't know. It's below the German. I'm misclicking everything today. Ignore it. Okay, so we'll select IS 1892002. If you're using the latest version, obviously select 2016. Okay, so and then click on add new function, and then you have to add the zone factor. So as per zone 5, our billing lies in zone 5, so the zone factor is 0.36. Find in the table attached here. Let me just show you very quickly this zone factor and thing, zone factor table. So everything is given here in the so just check out this notes here. Yeah, zone factor for seismic zone 5 is 0.36, so that's it. Table number 3 will find. So everything is mentioned in the notes, and soil type 2 is also mentioned in the notes where it's the table number. So just click on OK here, and okay, so we have defined the response spectrum function, overall response spectrum function. So now we have to define the model case here. So define here, and you have the model cases. So we'll just edit this existing thing here. So our it will be grid spectrum, and we'll add here in 3 directions the acceleration, because we'll applying the earthquake load in 3 directions. So this will be, this will be acceleration. So this will be the response spectrum load in 3 direction, ux, uy, and uz, and remaining things we keep as okay. Modal number of modes, if it doesn't satisfy our criteria, which I have just stated below the last part of the code, this document, I think, yeah, number of modes to be constant 7.7.5.2, then we change it. Otherwise you can keep it in a minimum of 12, or if it is multi-story building, then 3 per floor. Okay, you can do this initially, and later you can change as per the analysis results. So just click on OK, and OK once again, and then we'll add the response spectrum function in the load case. So go to define, and go to load cases. Here add new case, response spectrum. So it will be RSX response spectrum. We'll add the acceleration here. Scale factor, as we had discussed here, as per the CSI website, it is 0.981 in this case. So 0.98 we'll just add here. So we'll keep the methods, arithmetic methods, the same as CQC and SRS, SRSS, and we'll just click on OK, and we'll similarly add for the Y and the Z direction as well. Oh, just a misclick. Okay, so yeah, so having done this, now we'll go forward. So we'll add the columns here. So let's go, let's go to the plinth level here. Okay, 0, there's a plinth level. So we'll go to the select quick draw columns option, and then we select the column property here, which is this one. And you have to just look into the PDF which I provided you. Using that you can just assist. So 1, 2, 3rd and the 5th grid will have some columns here in the first row. So like this, row by row, you provide the columns here. Okay, 3rd and the 5th here, and then in the next grid here we'll have in the 1st and 2nd, 3rd, 5th and 6th. 1st, 2nd, only the 4th grid will miss out. So yes, pretty much same, only this grid will have this. And let me just check. Yeah, this 2 is the thing, it's not symmetrical or that kind. Okay, so I think I'll just skip this column part. Let me complete this. So as you can see, I've completed the columns here. So just click on escape here. Now we want to replicate this. So I'll use a 3D view. Use shift button and press the wheel button. Now press it, not press and hold it, to just rotate this. And I'll select all the columns here like this, because I don't want to select the supports here. And then when you select this, and then we'll go to Ctrl+R. This is a shortcut for replicate. Go to story and go to story, select solid story 3 and 4 and just hover over apply. Just don't click on it, just hover over apply and see that it is, what's the difference here. So just click on apply here and then click on OK. So yeah, I think for some reason this only one story got selected. Okay, so I'll just select this once again like this in this 3D view, and then I'll go to replicate once again, go to story, and this time only story 2. I'll hover over story 2, hover over apply and click on OK. So now it's complete. It should have been done in a single try. So that's my mistake. Okay, so no worries. So we'll go in the plinth level here and we'll complete the plinth beams. So we have the option of quick draw beams as well, and we'll use that option to draw the beams here. Be 300 into 450. So use this, join this, join this, join this like this, join this like this. As per the plan we have to do, right? So we are doing this like this. So it's always good to join the perimeters first, and join this like this. Okay, and all the primary beams which we can direct column to column connections which you can have, will have this. Yeah, this is very good in terms of shape. More column to column connections we have in the structure is better. Yeah, one extra we had made. Yeah, this is good, this is also good. Here, yeah, this beam is good, and we'll have some connections here over the slab above, and yeah, this connection also we can have. So yes, this is it. And the grids actually separate the some points here, some points here like this. So we'll just do this. So we select these, and also this one, also this one. So the grid actually divides it, but we want it to be single beam since there is no joints here, that's why. So yeah, this one also. So go to edit and go to edit frames and join frames. Now this single beams here. Similarly for this one also we'll do this one. Okay, now this is a single beam, this is a single beam, and this is a single beam. Okay, yes. Okay, this one is remaining, this one is also remaining, this one is also remaining. Okay, edit frames, join frames. Oh, I'll just press Ctrl+C because I want these two to be a beam and these two to be a beam. Okay, just yes. Now it's good. So you can select all the beams and replicate to the other floors. Okay, so for that you go to select select by properties, frame sections, and B 300 into 400, select this, and we'll press replicate control plus R, and then we'll go here by story. First of all, let me copy this to story 2, and then we'll go click on story 3 and go to select, get previous selection, and then we'll apply this to story 3. Click on OK. This is done. Yes, I think for the story 2 and story 3 there is one problem. We have to have a beam here, otherwise this particular slab will be too large. Or we can do this for this particular floor. So let's go in this particular floor here. This floor will have a slab, so we'll just add a beam here, add this beam here, and obviously it will get divided. Now it's fine. If you want to keep it this similar, you can just add another beam here as well. Okay, and let's add another one here as well. No issues. So we added one secondary beam just to reduce the span of the slab. Now in the span where we will have slab, in this one that is 3.9, we'll just add slabs here. Use this option, draw floor slab here. So, or you'll use the rectangular one option. So select, click here, left click, and don't release your click. And before doing this, just click this rectangular one and take the property to which we have defined slab 150 mm, like this. This portion has the staircase. Just to show you the staircase, there will be no slab above this portion, so you can leave this portion. Why does this doesn't have slab, beam here? We should have a beam here, right? This beam, we should have a beam here. Let me just check in the bottom floor as well. Yeah, we should have a beam here, the top floor as well. Yes. So that thing is fixed. Now let's go back to making slabs. Now this one is not perfect. This one is also not making perfect beams. I'll use the quick draw one for this one, this one, and this one. And for these ones, I'll just use the grid option. I think I should zoom and then do this better. Yeah, zoom and do this better, because that's how we do this. Still making mistake. Perfect. Now actually I lost my concentration due to a phone call, so I'll try to bring back my focus. Yeah, this is a work of focus, guys. This thing, you have to focus here. Cannot break your focus here. So the concentration level really matters here. It's done. Press Ctrl S once in, just to save this in once in a while, and then we go to 3D, and this is the look here. And let me go to plan here just very quickly, just to apply the fixed support here. Select all the bottom parts, assign joint restraints, and click on fixed and click on apply and click on OK. And after that we'll go to the 3D once again. Here let's start applying the loads here. So for the wind, we'll apply the wind panel. I think we can do this in last step. So first of all, let me apply the load of the walls here. So let's go here in the design considerations here. So always prepare your design considerations, because sometimes if the client tells a certain change, suppose, or you have to fix a certain thing 6 months, 2 months, 2 years, 3 years, then you can know the structural design calculation. From the structural design calculation you can remember what are the consideration which you had made. So yeah, enough things said. Let's go to the plan, plinth level. Select every beam here, some part have wall, some part doesn't have wall, so I'm just applying uniformly everywhere. Be on the safer side, obviously. Just making sure that every part is selected here. So you can go to plan view once again just to check. Yes, this part has been skipped. So we go to assign shell loads, frame loads, distributed. Here it will be the loads will be 17.25, so 17.25, and this will be another dead load. Obviously apply and click on OK, and then just go to the next floor, and in the next floor also, so you can select this beams here. I think we can deselect them later. The slabs we can deselect later. Let's deselect the slabs. So there is an option of select and deselect. You can also deselect the slabs from there as well. So you can try that also. Yeah, let's try that. This plan view, right? If I do like this, okay, does the column get selected? Let me just check in 3D view. Yeah, the columns also get selected. So if I go here, select and deselect by properties, and you go slab sections, slab 150, deselect, slab is deselected, and if I go select and deselect and by properties, frame sections, and I select the column property, then the column will get deselected. So yes, the columns are deselected now, but why are this selected then? Did the column deselection not work? See, yeah, this is selected. You can see select, deselect, object type, columns, deselect. Now it is working. Okay, so all the walls are selected. Now we'll go assign frame frame loads distributed. I'll go in other dead and 17.25, apply and OK. Okay, it's done. Now we'll deal with the topmost floor here. So the topmost floor, I think we can select the topmost floor like this. In this particular view, this will get the entire floor selected here, and we'll go assign and frame loads here distributed. For the truss, this is we are taking as 10 kN per meter, as you can see in the design considerations. Click on apply and click on OK. So then we'll select the slabs here. So go to select and select by object type, floors, select, and then we'll go assign shell loads uniform. So first of all, in the other dead load, floor finish load of 0.5 added, and then the in the live load we go select and get previous selection, and then the live load will add live load of 4 as per our design considerations, which you can see here, live load of 4 assembly restaurant. So click on apply and click on OK. Just for the verification, you can just see live load is already there. See display load as signs, shell load, dead, not dead, we'll add it in other dead, right? Apply. Yeah, you can see this load is there. So dead load, live load complete. Now seismic load, automatically we have defined all the parameters, so we are fine. So we're going to define load patterns here, modify load pattern. So we just want to check this out. So for this is for the x, seismic load in x direction, so y direction not required. Seismic zone 5.36, good. And always the seismic zone is calculated from the plinth level. Okay, considering y direction also, modify lateral load and plinth level. This is for the y direction, and okay. And for the wind load, this will be from shell objects, basic wind speed of 55, and terrain category 1. From the plinth level it will calculate it, also a lateral load. Click on OK. Okay, so we earthquake load part is completed. We only need to apply the wind load. For that we create some wind panels. Select this wind panel, and instead of this just select none property, because just simply we are looking for some point to apply the wind load. So you have to apply a rectangular way. Okay, just let's complete this. Okay, let me complete this, I think, off stream, because otherwise the video don't want the video to be too long. Just rotating and then completing the things here. Okay, so I've added all the wind panels here. So I can select all the wind panels here. So go to select by properties here, slab sections here, none, select. So the wind panels are selected here. Assign shell loads, wind pressure coefficients. So WL coefficient 1 will apply in the windward side. You can also add a new load case, wind load case, and apply in the leeward side as well, but it should be on the higher side, this one, wind load. And after the application of this, we'll press Ctrl plus S here, and we'll define some load combinations here. Add default load combination, concrete frame design, and then click on OK. And then we'll run the analysis here. By the way, till the analysis is run through Excel, you should ideally add the load combination as per the IS code here. So that thing has been missed, so we have to add some default load combination here. We can add some default load combination as per the IS code. Let me just show you this the clause of the particular load combinations here. So when you're using load combinations in 3 directions, so you should use this clause 6.3.1 here. You can see this is for the 2 directions, and this is for the, so in the default load combination, this this consideration, that is the full seismic load in 1 direction and 30% of the seismic load in other 2 directions, this doesn't happen in the default load combination, but we should add in the Excel. So I'll also make a video on this once I figure out the way of doing this using Excel. By the way, you can do this manually, but it will take a lot of time. So I'm just finding a shortcut to do this, and then I'll share with all of you guys. And if you guys have a shortcut, just share with me so that I can tell others. So we'll go with the analysis complete. We'll go with the concrete frame design. Our motto is to design the building, so I'll not show you the shear force, bending moment, etc. I'll show you the members of whether members are passed or not, and then how to give the final results to the draft person for the final structural drawing. Or if you want to make the final structural drawing, what are the things you'll consider? What is the size of the column? What is the reinforcement in the column? Those things are important. So those things we are focusing on right now in this particular video. So yeah, once this is done, what I'll do, I'll go to select and select by properties, slab sections, and both the slab 150 will select, and also the none also select, and I'll right click, and we'll go here. Okay, let me keep the slab only. Right click and then select, and after that right click and then hide selected objects to just ignore this. Okay, first focus will be on our columns here. So I can just do this, verify all member passed. So all members are passed, so we need to supply the reinforcement here. So the maximum reinforcement which you find, we'll just close this now. Maximum reinforcement which you'll find, we'll write this. So once the members are passed, so which means that our sizes are fixed. Okay, size for column is fixed and size for beam is fixed. Also we'll find out the maximum AST, or the area of steel required. So it's 1280 in this column which is visible. So we have to check all the columns one by one. I'll have another tricks as well, but let me just show you the basic method. All the columns one by one, that what is the maximum reinforcement in each columns. Okay, so maximum reinforcement visible is 1280, so we'll go here 1280. Now in 400 columns, with experience we know that we can easily accommodate 8 number of bars. So if you provide 8 bars of 16 mm, you go to pi by 4 into 16 square, so 1 bar area is 200 mm. So 8 into 200 is 1600. So we are providing more than what is required, so it is safe. So our final structural design will be column size 400 into 400, and the rods or the rebars will be 8 bars of 16 mm. Two types of rings will be there, which you already know. One will be diamond ring, and there will be rectangular ring. So then if you want to know in detail, we'll make another video. Just let me know in the comments if you want to know about the sizes as well. And then we'll have the beam size. So beam size, let's find out the maximum AST. So because the maximum amount of loads are applied in this pin level and this level, if we check these two floors, then it should be sufficient enough. So I'm giving a very simple design. If you want, you can just go make individual beams for each section as well, but I want to keep it simple for this particular project. So we'll go to plan and go to the plinth level. So check out the maximum AST which you have got. We have got an 807 here. And you can see everything is a range of 500 here, within the range of 500, 300. In fact, this is very low. So the higher reinforcement is this, I think they do to this secondary beam, but again you can see it is only at the edges. So at the center it is around 300, 400, only at the edges. So if you provide extra rebars, and then this will be able to manage. If you have so maximum is 807. So I'm just doing 859 here, because in the previous analysis I think I got 859 somewhere. Let me just go upwards here, because in the upwards we also have the floor finish load as well. So theoretically you might have some more AST anywhere. Okay, so you have to check this in detail, but I think this the result here will be the same. So let's say if 859 is the AST here, so we are considering the same rebar for both the bottom and the top of the this bottom and the top. By the way, you can see this is the top reinforcement, this is the bottom reinforcement. So we're considering the same, because typically you want to consider the same. At least the main reinforcement you consider same, and the extra you can just vary. So if you provide 316 all through, which means all through we'll have a AST of 3 into 200, which means 600. So you can see anywhere in the middle we have like everything is less than 600, so it should be okay. And at the ends, in some places we have 690. In this case, we go above 400. If you go the plinth beam, it will be higher. It will be 800 in this case. So for the ends, we can provide extra rebar, which will be at the ends of this. So it will be 316 if you do, then and plus 216 if you do, then it will be 2 into 200, which is 400. So you're providing an AST of 600 plus 400, which is 1000. So for this extra rebar diagram, I'm just showing you the diagram here. So this is a schematic diagram. You can see the extra top rebar here and extra top rebar here. This is usually applied at the ends. 0.1L for the discontinuous end, 0.3L for the continuous end, and the extra bottom rebar is applied at a distance of 0.1L from the discontinuous end and 0.25L from the continuous end. So it is applied in the extra bottom is applied to the middle, and extra top near the supports. So it is all due to the bending moment diagram here, which goes like this. So bending moment diagram for the fixed goes like this. So the maximum moments is at the supports for the top reinforcement, and the at the center for the bottom reinforcement. That's why the reinforcement extra rebars are placed like this. Okay, let's go back into our structure study. So this is done, and this after this is done, and then we can go for the beam design. So the beam design will be this 316 all through, both at the top and the bottom, and then we'll have 216 bars here. And for the footing design, we'll have to go do it manually, or we have to do with the help of an Excel sheet, or you can obviously use SAFE as well. but that part we can skip for this particular video, but I'll just show you how to get the particular value. So for that we'll go to 3D here, and we'll go to here, and we'll go to display show tables, and in the analysis, results, reactions, joint reactions. So we'll click on OK. So we'll copy this, we can copy this joint reaction here. You can see all are for the base here, so all the reactions are for the base for different loads and load combination. So just go into your folder whichever you want to create this. So let me just create a new Excel file here. Okay, so once you create a new Excel file, just paste it here, and this is the things which you don't need, you just delete those. And this is actually force in the X direction, Y direction, and Z direction. So only real force which you need is the force in the Z direction, so delete these two. And the moment also we need in the X and the Y, you don't need the moment in the Z direction. To solve numericals of footing design, you find that there are these three forces for which you have to design the footing. We check for one-way shear, two-way shear, and then design the footing. So here you just want to find the maximum of the force here, like this. I'll just see this is A2, right? The maximum cell number, you just check 2079 is the maximum cell number. So here I'll just do 2079, so maximum value I got. And also by copying this, I'll just get the minimum value as well, because magnitude doesn't matter if it is negative or different sign as well. It will show the same. In place of max, I'll do min, min, enter. And these two I'll copy to this cells here. So I get the maximum P, and then I'll get the mx and the my. So those have solved, those are students who have solved the numericals of footing design. They already know that these three values are needed. P you need, so P will be, let's say P will be, let's round it off to 1, 2, 4, 5, and this let's round it off to 69, and this let's round it off to 76. So here these are the files here, and then you can just put in any Excel sheet. I recommend you purchase an Excel sheet here, because I also purchased this, so I cannot give it to you since someone has worked hard for that Excel sheet. But using that Excel sheet you can do, and for learning you can always do manually as well. So this is in kilonewton, and this is in kilonewton per meter, and then you get the footing size results. You can match with my results. I got 2. No, I think it was safe in 2.4. So I got 2.5 into 2.5 at an SBC of 130. So then you have the retaining wall also. Retaining wall, so you can have design manually or using an Excel sheet which I had designed. So that's all for today's video. Hope you learned how something new today in this process, and you have found anything useful. Make sure to appreciate by hitting the like button, which helps the YouTube algorithm. Thanks for watching. Bye bye. Keep learning.